Chapter 1. Introduction. Man and the Stars. Since the dawn of mankind, the stars have captured people's imaginations. Long before telescopes, computers, and satellites existed, our ancestors looked up at the night sky and searched for orientation, meaning, and answers to the big questions. Where did we come from? Where are we going? And what is behind this endless sea of lights? For early humans, the sky was not just a sight, but a stage for myths, stories, and gods. Each culture created its own constellations, narratives, and interpretations. The chaos of sparkling dots in the sky became patterns, animals, heroes, or divine beings. The stars became signposts for sailors, calendars for farmers, and signs for priests and rulers. Astronomy, the oldest of all sciences. Astronomy is one of the oldest sciences of all. Long before mathematics or physics were practiced systematically, people began to observe the sky. As early as the Stone Age, people marked the positions of the sun and moon on stones or in cave paintings. Why? Because survival depended on it. Those who knew when winter would come or when to sow had an advantage. Thus, astronomy did not develop out of curiosity alone, but out of practical necessity. Heaven was a tool, a clock, a calendar. But at the same time, it was also an enigma, a mystery that made people think about their place in the universe. From myths to science. In the beginning, there were myths. The sunrise and sunset, the phases of the moon, the eclipses, all this was explained with gods. In Babylonia, for example, the planet Venus was the goddess Ishtar. In Greece, Helios was the sun god who pulled his chariot across the sky. But step by step, people began to recognize patterns that functioned independently of gods. They saw that the stars moved in regular orbits. They found that solar and lunar eclipses were predictable. Faith became knowledge, the birth of astronomy. This transition was not a sudden break, but a process. Myths and science often coexist. Even great astronomers such as Johannes Kepler still saw divine order in the movements of the planets. Heaven as a mirror of humanity. Astronomy is more than just observing the sky. It is a mirror of humanity itself. For farmers, it meant security, sowing at the right time. For seafarers, it meant orientation, the stars as signposts across the world's oceans. For rulers, it meant power. Whoever could interpret the signs of heaven had authority. For philosophers and scientists, it meant knowledge, the search for the laws of the universe. Heaven combined practical necessity, religious symbolism, and intellectual curiosity. Why we need heaven. To this day, astronomy has not lost its fascination. It is the science that most directly confronts us with the big questions. Are we alone in the universe? Did the universe have a beginning, and will it have an end? What is our position in the cosmic structure? Every new discovery, from Saturn's rings to the Milky Way to black holes, changes our self-image. Astronomy is therefore not only a natural science, but also a cultural science. It tells us something about ourselves. The journey begins. The history of astronomy is a journey that began thousands of years ago, with people looking at the starry sky and looking for patterns. It is a story of myths and mathematics, of errors and breakthroughs, of brilliant minds and courageous ideas. In the coming chapters, we will embark on this journey, from the first observations in the Stone Age, about the great cultures such as Babylonia, Egypt, and China, to the Greeks who revolutionized thinking, about the Middle Ages and the Copernican turn, to modern astronomy with space travel, black holes, and exoplanets. The stars have remained the same, but our understanding of them has changed radically. Conclusion. Heaven as an eternal companion. For as long as humans have existed, heaven has been their companion. He has guided us, nurtured, frightened, and inspired us. Astronomy is the story of this relationship between man and the cosmos. And even though we can now see billions of light years into space with telescopes, it all still starts with the same simple act. We look up and ask ourselves, what's out there? Chapter 2: Early Period and First Sky Observations. Looking at the sky is one of the oldest activities of mankind. Long before writing existed, people recognized patterns in the night sky, used the sun and moon to measure time, and interpreted unusual phenomena such as eclipses or comets as signs. Early astronomy was not yet a science in the modern sense, but a mixture of practical observation, religion, and mythology. But this was precisely where its significance lay. It laid the foundations for everything that came later. Sky observation in the Stone Age. The first evidence of astronomical practices dates back to the Stone Age. Nebra sky disk, ca. 1600 BC. Found in central Germany, it shows the sun, moon, and stars, an early attempt to symbolize the sky. Megalithic sites such as Stonehenge, c. 30,000–2000 BC. Stone circles in England and other parts of Europe were not only places of worship, but also astronomical calendars. The alignment with solstices and equinoxes shows that the course of the year was well known. Cave paintings. Some researchers suspect that Paleolithic representations of dots or patterns could already symbolize constellations. These early testimonies show that even the first advanced civilizations recognized that the movements in the sky were regular and predictable. Babylonians, masters of observation. The Babylonians, ca. 2500 BC, are considered the actual founders of systematic astronomy. They observed the sky for centuries and recorded everything in cuneiform script on clay tablets. They knew the planets, which they called wandering stars, and were able to predict their movements with astonishing accuracy. Her discovery of the Saros cycle, which can be used to calculate lunar and solar eclipses, is particularly famous. Astronomy and astrology were inseparable for the Babylonians. Celestial phenomena were considered messages from the gods, especially for the king. Nevertheless, they laid the foundations for mathematical predictions that still influenced the Greeks. Egypt, heaven and religion. The Egyptians also used the sky intensively. The Sirius observation was central. The heliacal rising of the star announced the annual Nile flood, vital for agriculture and survival. They developed a calendar with 365 days based on solar and star observations. Monuments such as the pyramids of Giza or temples in Karnak are often astronomically oriented, for example after solstices. For the Egyptians, heaven was closely associated with religion. Pharaohs were considered children of the sun, and heaven was the domain of gods such as Ra or Nut. Astronomy in China. Independent of Babylon and Egypt, a rich astronomical tradition also developed in China. As early as 2000 BC, Chinese astronomers were conducting celestial observations. They were particularly good at recording celestial events, solar and lunar eclipses, comets, supernovae. One of the earliest known supernovae, 1054 AD, is documented in Chinese chronicles and led to the formation of the Crab Nebula. Chinese astronomy was strongly oriented towards the practical use of calendars and rule. Whoever interpreted the sky proved that he possessed the mandate of heaven. India, cosmos and philosophy. Astronomy also played an important role in ancient India. Indian astronomers created star catalogs early on and developed mathematical methods for calculating planetary motions. Vedic astronomy combined cosmological considerations with rituals. Later, works such as the Siddhantantas were created in India, which contained detailed models of celestial mechanics. India produced a close connection between astronomy and mathematics, which later influenced Arab and European scholars as well. Astronomy in Central and South America. The cultures of the Americas also had sophisticated observations of the sky, independent of the Old World. The Maya developed a highly precise calendar based on observations of the sun, moon, and planets. Temples and pyramids, for example in Chichen Itza, are astronomically oriented, for example to the solstices. The Incas also used celestial observations for agriculture and religion. For these cultures, astronomy was closely linked to religion and rituals, similar to Egypt and Babylon. Commonalities of early astronomy. Whether in Babylon, Egypt, China, India, or the Maya, the early astronomy had a lot in common. Calendar function. They were used to predict the seasons. Religious interpretation. Celestial phenomena were considered messages from the gods. Practical use. Agriculture, seafaring, and politics depended on celestial observations. Long-term observation. Data was collected over generations that later became the basis for mathematical models. Transition to theory. While the early cultures mainly observed, the Greeks later began to look for explanations. Instead of just registering patterns, they asked, why do the stars move the way they do? Are the planets bound to spheres? Is the Earth the center, or does it move itself? This marked the beginning of the transition from practical astronomy to theoretical astronomy, and thus to science in the true sense of the word. Conclusion: heaven as primordial teacher. The early days of astronomy show that the sky was man's first teacher. He taught us to measure time, understand nature, and question our position in the cosmos. Even without telescopes or modern physics, early cultures discovered amazingly precise laws. To this day, their observations form the foundation on which modern astronomy rests.
Chapter 3: The Greeks and the Birth of Theoretical Astronomy. While the early advanced civilizations of Babylon, Egypt, China, or India mainly observed the sky and developed practical applications such as calendars and rituals, the Greeks did something new. They began to interpret the cosmos theoretically. Instead of just registering patterns, they asked questions about causes, principles, and laws. This made astronomy a real science, combined with mathematics, geometry, and philosophy. From myth to philosophy. In the early Greek period, celestial phenomena were still closely associated with myths. The gods of Olympus were identified with planets, constellations, and natural phenomena. But from the 6th century BC onwards, an upheaval in thinking began in the Greek city-states. Philosophers such as Thales of Miletus searched for rational explanations for natural phenomena. Thales is said to have predicted a solar eclipse. Anaximander designed a cosmological idea with the Earth as a free-floating cylinder. Anaximenes saw air as a primordial principle that also determined the movements of the sky. These early approaches were still speculative, but they marked the transition from a mythical worldview to a philosophy of nature. Pythagoras and the harmony of the spheres. Pythagoras, 6th century BC, brought the idea that celestial movements follow mathematical laws. He saw the planets as bound to spheres that produce harmonious sounds, the famous harmony of the spheres. This combination of mathematics, music, and the cosmos had an enormous effect. The sky was understood as an ordered, calculable system. Even though the theory had a mythological touch, it paved the way for mathematics as the basis of astronomy. Aristarchus of Samos, a forgotten revolutionary. In the 3rd century BC, Aristarchus of Samos ventured a sensational hypothesis. He placed the sun at the center of the cosmos and explained that the Earth revolves around it. This made him the first known representative of a heliocentric view of the world, 1800 years before Copernicus. But his idea did not catch on. Why? The apparent movement of the sun and stars spoke against him. There was a lack of evidence such as parallax, the displacement of stars due to the Earth's movement. Aristotle's and Ptolemy's authority secured the geocentric view of the world. Aristarchus remained a lonely visionary, but he shows how early revolutionary ideas were formulated. Aristotle and the geocentric worldview. Aristotle, 384 to 322 BC, was one of the most influential thinkers ever. He saw the Earth as the resting center of the cosmos. The planets and stars are attached to crystalline spheres that move in perfect circular orbits. The world is divided into a sublunar sphere, below the moon, imperfect, changeable, and a supralunar sphere, above, perfect, eternal, unchangeable. This worldview combined philosophy, physics, and theology. It was the dominant model for over 1,500 years, even in the Middle Ages. Hipparchus, the master of observation. In addition to the philosophers, there were also astronomers who made meticulous observations. Hipparchus of Nicaea, the 2nd century BC, is considered one of the greatest observers of antiquity. He created the first star catalog with over 1,000 stars. He discovered the precession of the Earth's axis, a slow shift in the celestial axis over thousands of years. He developed trigonometric methods to mathematically calculate celestial movements. Hipparchus was the practical astronomer, while Aristotle provided the theoretical basis. Plotinus and the standard model of antiquity. The high point of Greco-Roman astronomy was Claudius Plotinus, the 2nd century AD, with his work Almagest. He combined the geocentric view of the world with a mathematical model. Planets moved on epicycles, small circles, which in turn moved on larger circles, deferents, around the Earth. This allowed him to predict the planetary movements very precisely, despite the wrong basic assumption. The Ptolemaic worldview was so successful that it was considered valid for over 1,400 years, until Copernicus shook it. Philosophy and astronomy, hand in hand. Greek astronomy was closely linked with philosophy. Cosmos meant order, harmony, mathematical beauty. Circular movements were considered perfect and divine. Science was not only observation, but also the search for an ideal view of the world. This way of thinking was formative and also an obstacle. Because the circle was adhered to as the perfect form, it took a long time for elliptical orbits to be accepted. Heritage of the Greeks. The Greeks laid the foundations of theoretical astronomy. They combined mathematics and celestial observation. They developed the first models of the cosmos. They asked questions that are still relevant today. Is the Earth the center? What laws determine the celestial movements? Their legacy was taken up and further developed in late antiquity and the Middle Ages by Islamic and later European science. Conclusion: the beginning of science. The Greeks made astronomy what we call a science today. They broke away from pure observation and asked about causes, principles, and mathematical order. Even if many things were wrong, they laid the foundation on which Copernicus, Kepler, Galileo, and Newton could later build.
Chapter 4. Astronomy in the Middle Ages. The Middle Ages were an era of transition. While Greek astronomy had laid the foundation, in the Middle Ages it was mainly the preservation, transmission, and adaptation of knowledge that determined the course. Contrary to the cliché of the Dark Ages, astronomical knowledge was not forgotten during this period. On the contrary, science flourished in the Islamic world, new mathematical methods were developed in India, and the foundations for the later Copernican revolution were laid in Europe. Preservation by the Islamic world. After the fall of the Western Roman Empire, 476 AD, the center of knowledge shifted. In the Islamic world, the works of Ptolemy, Aristotle, and other Greek scholars were translated and commented on. Centers such as Baghdad, Damascus, and Cairo became strongholds of astronomy. In the 9th century, the Caliph al-Ma'mun founded the House of Wisdom, Beit al-Hikmah in Baghdad, where translations and new research were carried out. Important Islamic astronomers. Al-Battani, 850 to 929, refined Ptolemaic models and determined the length of the solar year very precisely. Alhazen, 965 to 1040, pioneer of optics, whose work later influenced Galileo's telescope experiments. Nasir al-Din at-Tusi, 1201 to 1274, developed the Tusi couple, a mathematical model that later reappeared in Copernicus. Islamic astronomy combined Greek tradition with Indian and Persian influences and produced precise measurements. Astronomy in India. The astronomical legacy was also continued in India. The Siddhantas, astronomical manuals, combined mathematical calculations with observations.
Indian scholars introduced trigonometric functions such as sine and cosine, which became crucial for calculating planetary orbits. Works such as the Surya Sahanta, ca. 5th century, contained surprisingly precise information on the rotation of the Earth, solar and lunar eclipses. These findings later influenced Islamic and thus indirectly European astronomy. Europe in the early Middle Ages. Preservation by monasteries. In Europe, astronomy was initially strongly associated with the Church. Monasteries preserved ancient writings and used astronomy to calculate the church calendar, e.g. Easter date. Looking at the sky was not only science, but also theology. The sun and stars were considered divine creation. Many monasteries had small observatories or used sundials to determine the times of day for prayers. Although Europe lagged behind the Middle East in terms of science, ancient knowledge was not completely lost. Scholasticism and the universities. From the 12th century onwards, a renaissance of knowledge began in Europe. Ptolemaic and Aristotelian texts reached Europe through translations from Arabic. Universities such as Paris, Bologna, and Oxford included astronomy in the curriculum. Scholars such as Albertus Magnus and Thomas Aquinas tried to unite the geocentric worldview with Christian theology. The geocentric model was still taken for granted, but the discussions about details became more and more subtle. Instruments and observations. In the Middle Ages, astronomical instruments were also improved. Astrolabe, a portable device for determining star positions and navigation. Quadrant and armillary sphere, tools for more precise measurements. Star catalogs from Arabic and European sources improved the accuracy of the data. These instruments prepared the ground for the Great Revolution of the early modern period. Conflicts with theology. Astronomy in the Middle Ages was closely intertwined with theology. The Bible was considered truth, and astronomical models had to subordinate themselves to it. Theological interpretations, such as the story of creation, determined how celestial phenomena were explained. Nevertheless, there was room for discussion. Some theologians accepted astrology as the language of God. The tension between faith and science was therefore not as rigid as it is often portrayed, but transitioned to the modern age. At the end of the Middle Ages, astronomy had reached a point where observation and theory were precise but deadlocked. The Ptolemaic worldview prevailed unchallenged, although it became increasingly complicated, with more and more epicycles to explain deviations. Observations of planetary motions raised doubts, but a new paradigm was missing. The translations of ancient and Arabic writings to Europe prepared the basis for the coming turning point. Conclusion: the Middle Ages as a bridge. The Middle Ages were not a time of stagnation, but a bridge between antiquity and modern times. In the Islamic world, astronomy reached new levels of precision. Important mathematical tools were created in India. In Europe, knowledge was preserved, systematized, and finally rediscovered. The Copernican revolution of the 16th century would not have been conceivable without these foundations.
Chapter 5. The Copernican Turn. The Copernican turn was one of the most significant revolutions in the history of science. It not only turned the image of the cosmos upside down, but also shook the intellectual, religious, and social foundations of Europe. With the idea that the sun is at the center of the universe and not the Earth, a new age of astronomy and modern science began. The problem of the Ptolemaic system. For over 1,000 years, the Ptolemaic worldview dominated. The Earth stood motionless in the center. The sun, moon, and planets moved around them in epicycles, small circles on large circles. This model was mathematically sophisticated and could explain observations well. But there were problems. Increasingly complex deviations in the planetary motions required additional epicycles. New observations made the system appear increasingly unwieldy. The impression was created that the model was more of a computational tool than a true representation of the cosmos.
In the 15th century, the geocentric worldview was officially untouched, but it was already crunching at its foundations. Nicolaus Copernicus, the quiet revolutionary. Nicolaus Copernicus, 1473 to 1543, was a canon, physician, lawyer, and, above all, astronomer from Turin, now Turin, Poland. From an early age, he was involved in ancient astronomy. On his study trips, he became acquainted with the knowledge of Arab and European scholars. He began to work on a new model that would overcome Ptolemy's disagreements. His idea was radical. The Earth moves around the Sun. The heliocentric view of the world. In his main work, De Revolutionibus Orbium Celestium, On the Orbits of the Celestial Bodies, 1543, Copernicus presented his new model. The core ideas. The Sun in the center. Not the Earth, but the Sun is the center of the universe. The Earth as a planet. The Earth revolves around the Sun and also around its own axis every day. The planetary orbits. The other planets also orbit the Sun in circular orbits. The Moon. Only the Moon continues to orbit the Earth. This model explained many phenomena more simply than the Ptolemaic one. The retrograde of the planets, apparent loops in the sky, was no longer a complicated movement but a perspective effect due to the movement of the Earth. The brightness fluctuations of the planets resulted logically from their different distances from Earth. Why Copernicus hesitated? Copernicus published his work only shortly before his death. He feared the resistance of the Church and the scholarly world. His model, while elegant, had little empirical evidence. It was not yet superior. The retention of circular railways continued to complicate things. His work was initially considered by many to be a purely mathematical hypothesis, not a physical reality. First reactions. Reactions to the Copernican worldview were mixed. Some scholars saw this as a useful calculation aid. Others rejected it because it contradicted the sensory experience. You couldn't feel that the Earth was moving. Theologians criticized that it contradicted biblical statements, e.g., Joshua 10, "Sun, stand still." Despite resistance, the work began to circulate and inspired a new generation of astronomers. Tycho Brahe, the observer. Tycho Brahe, 1546 to 1601, was one of the greatest observers in the history of astronomy. He built the Uraniborg Observatory on the island of Heaven, the most modern of its time. He created extremely precise star catalogs, even without a telescope. He discovered a new star, supernova of 1572, and proved that the sky was not immutable. Tycho rejected the heliocentric model and developed a hybrid model. The planets orbited the Sun, but the Sun orbited the Earth. However, his observations became the basis for Kepler's discoveries. The significance of the Copernican turn. The Copernican turn was not only a scientific event, but also a cultural one. Humans lost their central position in the cosmos. The Earth was just one planet among many. The authority of ancient thinkers, such as Aristotle, was questioned. A new way of thinking prevailed. The laws of nature could be researched independently of tradition and religion. This was the beginning of modern science, empirical, critical, open to radical ideas. Aftermath. Even though Copernicus himself did not live to see the revolution, his work was the spark that changed everything. Johannes Kepler used Tycho's data to discover the laws of planetary motion. Galileo Galilei used the telescope to confirm the correctness of the heliocentric model. Finally, Isaac Newton used gravity to explain why the planetary orbits were as they were. Without Copernicus, none of this would have been conceivable. Conclusion: the beginning of a new era. The Copernican turn was more than a new astronomical model. It was a spiritual revolution that changed the world view of mankind. It shifted the center from man to the sun. It turned the Earth into a planet, and thus the universe larger and stranger. It initiated a development that continues to this day, the urge to understand the cosmos rationally. Copernicus was a quiet revolutionary, and his work a milestone on the way to modernity.
Chapter 6: Kepler and Galileo, the Revolution of Heaven. Copernicus's ideas turned the worldview upside down, but they needed evidence to really prevail. This evidence was provided by two men, Johannes Kepler, who described the movements of the planets mathematically, and Galileo Galilei, who looked directly into the sky with the newly invented telescope. Together, they brought the Copernican turn from theory to reality and ushered in a true scientific revolution. Johannes Kepler, the mathematician of heaven. Johannes Kepler, 1571 to 1630, was a German astronomer, mathematician, and natural philosopher. Even as a young man, he was enthusiastic about the heliocentric model. In 1600, he entered the service of Tycho Brahe to mathematically evaluate his observations. After Tycho's death, he took over the data and found the keys to the truth in it. Kepler's three laws. First law, 1609. The planets do not move in circles, but in ellipses, with the sun at a focal point. Second law. A planet sweeps over the same areas in the same time. This means that it moves faster when it is closer to the sun. Third law, 1619. The relationship between orbital period and orbital magnitude follows a fixed mathematical relationship, t squared to r cubed. These laws were revolutionary. For the first time, the movements of the planets were described by simple mathematical rules, without epicycles and spheres. Kepler's vision. For Kepler, astronomy was more than mathematics. It was a divine harmony. He believed that God had created the cosmos according to mathematical principles. His search for the laws was at the same time a search for divine order. He was convinced that mathematics is the language in which the universe is written. In doing so, he combined religious conviction with modern science, a bridge between the Middle Ages and modern times. Galileo Galilei, the observer with the telescope. While Kepler found the mathematics of the heavens, Galileo Galilei, 1564 to 1642, opened up a new dimension with the telescope. He built one of the first astronomical telescopes in 1609. With his observations, he shook the foundations of the geocentric view of the world. Galileo's discoveries. Mountains and craters on the moon. The moon was not perfect and smooth, but shaped like the Earth. Moons of Jupiter, 1610. 4 moons orbited Jupiter. Not everything orbited the Earth. Phases of Venus. They could only be explained in the heliocentric model. Sunspots. The sun was also not perfect, but changeable. These observations showed that Aristotle's idea of a perfect, unchanging sky was wrong. Conflict with the Church. Galileo was a passionate advocate of the Copernican system. In 1616, the heliocentric model was condemned by the Catholic Church as heretical. Galileo was only allowed to teach it as a mathematical hypothesis. In 1632, however, he published the Dialogue on the Two World Systems, a skillful defense of heliocentrism. He was then brought before the Inquisition in 1633. Galileo had to abjure publicly. He was sentenced to life imprisonment. Nevertheless, his ideas spread inexorably. Different roles, but the same effect. Kepler and Galileo complemented each other perfectly. Kepler provided the mathematical laws of planetary motion. Galileo provided the empirical observations that supported the heliocentric view of the world. Together, they gave the Copernican model a solid basis. Without Kepler, Galileo's observation would have been patchy. Without Galileo, Kepler's laws would have remained abstract mathematics. The beginning of modern science. With Kepler and Galileo, a new era began. Observation and mathematics became the central methods. Authorities such as Aristotle or Ptolemy lost importance. The idea prevailed that nature can be explained by universal laws. Astronomy had thus finally become a modern natural science. Conclusion: the revolution of the sky. The work of Kepler and Galileo brought the Copernican revolution to a breakthrough. Kepler showed that planets do not run in perfect circles, but in mathematically describable ellipses. Galileo proved with the telescope that the sky was not perfect and unchanging. Together, they turned a controversial hypothesis into a new worldview. The Earth was no longer the center of the universe, and man was no longer the center of creation. It was the beginning of a new epoch of science and philosophy.
Chapter 7: Newton and Gravity. The discoveries of Kepler and Galileo had revolutionized the worldview, but one crucial question remained unanswered. Why do the planets move the way they do? Why do they follow Kepler's laws? Why does an apple fall to Earth while the moon remains in the sky? The answer was provided by Isaac Newton, 1643 to 1727, and with it, one of the greatest scientific achievements in human history. Newton's life, from farmer's son to universal genius. Isaac Newton was born in 1643 in Woolsthorpe, England. As a child, he grew up without a father and was initially considered inconspicuous. At the University of Cambridge, he discovered his talent for mathematics and natural philosophy. In the 1660s, during a plague epidemic, he withdrew to the countryside and developed ideas there that were to change the world. Newton was not only an astronomer, but also a mathematician, physicist, alchemist, and theologian, a polymath in the spirit of the Renaissance. The Principia Mathematica, 1687. In 1687, Newton published his main work, Philosophia Naturalis Principia Mathematica. In this work he combined Kepler's laws of planetary motion, Galileo's mechanics of falling bodies, his own theory of gravity. In doing so, he created a uniform explanation for the movements on Earth and in heaven. The law of gravitation. Newton's central insight was the law of universal gravitation. Each body attracts every other body with a force. This force is proportional to the product of its masses. It decreases with the square of the distance. Formula: F equals G times m1 times m2 divided by r squared. This meant that the force that makes an apple fall is the same that keeps the moon on its orbit. Significance of the theory of gravity. Newton's gravity was revolutionary. For the first time, there was a universal law that applied to all bodies, on Earth as well as in the cosmos. The universe became a mechanical system that functions according to mathematical rules. Mystical explanations became superfluous. Astronomy thus finally became an exact natural science. Newton's mechanics. In addition to gravity, Newton also formulated the three laws of motion. A body remains at rest or in uniform motion as long as there is no force. Force equals mass times acceleration. F equals ma. Actio-reactio. Every force has an equally large opposing force. These laws are still considered the basis of classical physics today. Newton's synthesis. Newton achieved something unique. He combined the knowledge of thousands of years in a unified system. Of the Babylonians, long-term observations. From the Greeks, mathematical models of the cosmos. Von Copernicus, das heliocentric Weltbild. Von Kepler, mathematical laws of planetary motion. Von Galileo, Experimente zur Mechanik. Newton put all this together into a cosmic blueprint. Criticism and limits. Although Newton's theory was successful, there were also open questions. He couldn't explain how gravity works, only that it works. I don't invent hypotheses. The image of a clockwork universe was powerful, but left little room for uncertainty or dynamism. It was not until Einstein that gravity was re-explained as the curvature of space and time. Influence. Newton's work shaped science and philosophy for centuries. It inspired the Enlightenment with the idea that nature can be explained by reason. It led to the development of modern technology and engineering. His image of the universe as precise clockwork shaped thinking until the 19th century. Newton became an icon, almost mythically revered, as the man who found the laws of the universe. Conclusion: the architect of the cosmos. With Newton, astronomy reached a new peak. He gave a universal explanation to the movements of the planets and stars. He connected heaven and earth by a single law of nature. He made nature predictable and opened the way for modern physics and technology. Newton transformed the universe into a mathematically describable system, a cosmos accessible to the mind. In doing so, he set a milestone that can only be compared to Einstein's achievements.
Chapter 8: Astronomy in the Age of Enlightenment. The 18th century, often referred to as the Age of Enlightenment, was characterized by reason, science, and belief in progress. After Newton's great synthesis, astronomy continued to develop, now with a new self-image. The cosmos was no longer a mysterious realm of the gods, but a mechanical system that could be understood through observation and mathematics. Astronomy became a leading science of the Enlightenment. Newton's legacy. The generations after Newton saw his theory of gravity as the key to explaining the universe. The planetary orbits could now be calculated precisely. Comets were no longer understood as harbingers of doom, but as predictable celestial bodies. The image of a clockwork universe shaped the entire era. The world as a machine, created according to mathematical laws. Astronomy stood for rationality and for the power of the human mind. New observatories and measuring instruments. In the 18th century, astronomy experienced an upswing due to better instruments. Telescopes became more powerful, for example through mirror constructions by William Herschel. More precise clocks allowed more precise time measurements, important for navigation and sky observation. Observatories were built all over Europe, from Greenwich to Paris, from Berlin to St. Petersburg. These institutions made astronomy an institutionalized science with fixed structures. William Herschel, discoverer of a new planet. An outstanding astronomer of the Enlightenment was William Herschel, 1738 to 1822. Originally a musician, he built his own large reflecting telescopes in England. In 1781, he discovered the planet Uranus, the first planet discovery since ancient times. He catalogued nebulae and star clusters and thus laid the basis for galaxy research. Together with his sister Caroline Herschel, he created comprehensive star maps. Herschel's work showed that the cosmos is much larger and more diverse than previously thought. Astronomy and navigation. Astronomy was not only theoretical but also practical. The determination of longitude was a central problem of seafaring. In the 18th century, John Harrison invented precise marine chronometers, which, in combination with astronomical methods, made it possible to determine an exact position. This made astronomy a driving force of global trade and seafaring. Comets, stars, and order of the sky. The Enlightenment also brought new insights into the nature of celestial bodies. Edmund Halley realized that comets have recurring orbits. Halley's comet, named after him, appeared in 1682 and returned in 1758, as he had calculated. Stars were no longer seen only as points in the sky, but as distant suns. The first hypotheses about the formation of nebulae and star clusters emerged, early precursors of modern astrophysics. Philosophy and cosmos. Astronomy also shaped the thinking of the Enlightenment. Immanuel Kant developed the nebular hypothesis. Stars and planets form from rotating clouds of gas and dust. Philosophers such as Voltaire or Diderot saw astronomy as proof of the power of reason. The universe seemed infinite and full of worlds, an idea that made man small, but at the same time inspired him. Astronomy was not only science, but a symbol of freedom and enlightenment. The democratization of knowledge.
In the Age of Enlightenment, astronomy became popular. Books, maps, and celestial atlases made knowledge accessible. Civil societies organized observatories and public lectures. Amateurs also took part in observations. Astronomy became part of general education. The stars no longer belonged only to priests or kings, they became the heritage of humanity. Conclusion: astronomy as the guiding science of reason. In the 18th century, astronomy was a symbol of the ideals of the Enlightenment. It showed the power of reason to recognize order in the universe. It combined theory and practice, from philosophy to navigation. She opened her eyes to the infinity of the cosmos. Enlightenment astronomy was thus not only a science, but a cultural model, and the stage for the next great phase, the birth of modern astrophysics in the 19th century.
Chapter 9: The 19th Century, Spectroscopy and Astrophysics. The 19th century brought a new dimension to astronomy. It transformed from pure celestial mechanics into a physics of stars. With the development of spectroscopy and new observational techniques, astronomers have been able to study the chemical composition, temperature, and motions of stars and nebulae for the first time. This gave rise to astrophysics, the combination of astronomy and physics that revolutionized the understanding of the universe. From celestial mechanics to stellar physics. Until the 18th century, astronomy was primarily the art of calculation. The aim was to predict planetary orbits, calculate comets, and create celestial maps. But in the 19th century, the goal changed. They wanted to know not only where celestial bodies move, but also what they are. Stars were no longer seen as anonymous points of light, but as physical objects with temperature, mass, and chemical composition. Astronomy was transformed into a natural science in the modern sense. The invention of spectroscopy. The key to this revolution was spectroscopy. In 1666, Isaac Newton had broken down sunlight with a prism and shown that it consists of a spectrum of colors. In the 19th century, Joseph von Fraunhofer and others investigated this spectrum in more detail. Fraunhofer discovered the dark lines in the solar spectrum, which were later interpreted as absorption lines of atoms. This made it clear that the light of the stars carries information about their composition. Chemistry of the stars. With spectroscopy, astronomers have now been able to find out what stars are made of. In the 1860s, Kirchhoff and Bunsen realized that each chemical element has a specific line spectrum. By comparing these laboratory spectra with the light of the sun or other stars, their chemical elements can be identified. Sensation! Stars consist of the same elements as the Earth, mainly hydrogen and helium. For the first time, the bridge was built between terrestrial chemistry and cosmic astronomy. Stars as physical objects. The new methods made it possible to systematically study stars. Temperature. The surface temperature could be derived from the color of the light. Motion. The Doppler effect allowed astronomers to determine whether a star is moving towards or away from us. Structure. Initial models described stars as spheres of gas held together by gravity. This marked the beginning of research into stellar evolution, from birth in nebulae to death as a white dwarf or supernova. Discovering new worlds. The 19th century also brought many concrete discoveries. Neptune, 1846, discovered by calculating orbital perturbations of Uranus, a triumph of Newtonian mechanics. Asteroids, hundreds of small bodies between Mars and Jupiter have been found. Binary stars. More and more star systems have been recognized as pairs, which has brought new insights into mass and gravity. The diversity of the sky became more and more apparent. Women in astronomy. The 19th century also brought the first systematic contributions of women to astronomy. Caroline Herschel discovered several comets and worked closely with her brother William. Later in the century, researchers such as Annie Jump Cannon and Henrietta Leavitt emerged to make fundamental contributions to classification and cosmology by analyzing stellar spectra and brightness. Although women were often overshadowed by their male colleagues, they laid important foundations for modern astrophysics. Astrophysics as a new discipline. In the second half of the 19th century, the term astrophysics was coined. Observatories set up physical laboratories to analyze the light. Astronomy was more closely linked to physics, chemistry, and mathematics. Astronomy was no longer just celestial mechanics. It became the science of the stars. Astronomy and society. In the 19th century, astronomy also became more attractive to the public. Large observatories such as those in Paris, Berlin, or Greenwich became symbols of national pride. Popular science books and public lectures made the stars accessible to a wide audience. The idea of an infinite, physically explainable universe influenced philosophy, art, and literature. Conclusion: the beginning of modern astrophysics. The 19th century transformed astronomy from a calculating discipline to an explanatory science. With spectroscopy, astronomers were able to decipher the chemical composition of the stars. New discoveries such as Neptune and numerous asteroids showed the diversity of the sky. The birth of astrophysics laid the foundation for the great revolutions of the 20th century, from the theory of relativity to the Big Bang. The stars were no longer unattainable lights. They became physical objects, the secrets of which man revealed step by step.
Chapter 10. The 20th Century. Expansion of the Universe. The 20th century brought an even deeper revolution than Copernicus or Newton. The realization that the universe is not static, but dynamic and expanding. With Einstein's theory of relativity, Hubble's observations, and the discovery of the cosmic background radiation, our image of the cosmos changed fundamentally. Astronomy became cosmology, the science of the entire universe. Einstein and the theory of relativity. In 1905, Albert Einstein published the special theory of relativity. Space and time are not separate, but form a four-dimensional space-time continuum. Nothing moves faster than light. Mass and energy are equivalent. E equals mc squared. In 1915, the general theory of relativity followed. Gravity is not a force in the Newtonian sense, but a curvature of space-time. Mass deforms space, and bodies move along this curvature. This could be used to explain the movement of the planets, the deflection of light at stars, and even black holes. The theory of relativity opened up completely new perspectives on the cosmos. The problem of the static universe. Einstein himself initially believed in a static universe, but his equations pointed to a dynamic, expanding universe. To avoid this, he introduced a cosmological constant, a kind of counterweight to keep the universe stable. Later, he called this his greatest foolishness. The observations should soon show that the universe is indeed in motion. Edwin Hubble and the galaxies. In the 1920s, Edwin Hubble worked at the Mount Wilson Observatory in California. With the 2.5-meter Hooker telescope, he was able to look into the depths of the universe. He discovered that the nebulae in the sky are actually other galaxies far outside the Milky Way. This made the universe immeasurably larger than anyone had ever thought. The expansion of the universe. Hubble went even further. He measured the redshift of light from distant galaxies. The result? The further away a galaxy is, the faster it moves away from us. This led to the formulation of Hubble's law in 1929. V equals h0d. Speed is proportional to distance. The universe is expanding, a revolutionary idea that destroyed all ideas of a static cosmos. The Big Bang. The expansion led to an obvious conclusion. If the universe is expanding, it must have once been smaller. The Belgian physicist Georges Lemaitre developed the theory of the primordial atom, an initial state of the universe. Later, the term Big Bang prevailed. The Big Bang theory explained time, space, and matter came into being together in an initial moment about 13.8 billion years ago. Rivalry of theories. In the 20th century, two models competed. Big Bang theory, universe has a beginning, has been expanding ever since. Steady-state theory, Hoyle-Bondi and Gold, universe is expanding, but new matter is constantly being created, so it looks the same forever. The decision brought a sensational discovery in the 1960s. The cosmic background radiation. In 1965, Arno Penzias and Robert Wilson accidentally discovered a faint noise with their radio antenna. It was the cosmic microwave background radiation, an echo of the Big Bang. It dates back to the time when the universe was about 380,000 years old and became transparent. This discovery confirmed the Big Bang theory and refuted the steady-state theory. With this, the modern image of the universe was born. Black holes and exotic objects. The 20th century also brought new insights into extreme celestial bodies. Black holes, previously theoretical, now confirmed by observations. Quasars, extremely luminous cores of distant galaxies powered by black holes. Neutron stars and pulsars, discovered by Jocelyn Bell in 1967, stellar remnants with enormous density. The universe turned out to be much more exotic than anyone had ever believed. Telescopes and technology. The technical development of the 20th century revolutionized astronomy. Radio telescopes opened up the view of invisible radiation. Satellites such as Hubble, 1990, made it possible to observe the Earth's atmosphere. New wave ranges, from infrared to X-rays, provided insights into unknown processes. Astronomy became interdisciplinary and international. Philosophy and culture. The expansion of the universe also had philosophical consequences. Man realized that he lives in a temporally finite cosmos. Questions about the beginning and end of the universe influenced religion, philosophy, and art. Science fiction literature enthusiastically took up the ideas of the Big Bang, black holes, and galaxy flights. Conclusion: the century of cosmology. The 20th century transformed astronomy into cosmology. Einstein provided the foundation with the theory of relativity. Hubble showed that the universe is expanding. The discovery of the background radiation confirmed the Big Bang. New telescopes and techniques revealed the diversity and strangeness of the cosmos. The universe was no longer static and eternal. It had a history, an origin, and possibly an end.
Chapter 11: Space Travel and Modern Astronomy. The 20th century brought not only new theories about the universe, but also the technical ability to penetrate into space itself. With space travel, astronomy changed from a purely observational science to an active exploration of the cosmos. Satellites, space probes, and manned missions opened up a view that was previously unimaginable. Since then, modern astronomy and space travel have been closely intertwined. The beginnings of space travel. The idea of reaching space goes back a long way, but it wasn't until the 20th century that it became reality. In 1903, Konstantin Tsiolkovsky published a theoretical treatise on rocket technology in Russia. In the 1920s and 1930s, researchers such as Hermann Oberth and Robert Goddard experimented with liquid rockets. During the Second World War, the V-2 rocket was the first rocket that could cross the border into space. After the war, a new chapter began, the space age. The space race. The 1950s and 1960s were marked by the Cold War and the space race between the USA and the Soviet Union. 1957, the Soviet Union launched Sputnik 1, the first artificial satellite. 1961, Yuri Gagarin became the first man in space. 1969, Apollo 11 was the first time that humans landed on the moon. These milestones were not only political prestige projects, but also provided valuable scientific data.
Satellites and telescopes in space. A decisive step was the use of space telescopes. Hubble Space Telescope, 1990. Observations without a disturbing Earth's atmosphere enabled images of unprecedented sharpness. Hubble provided evidence of the expansion of the universe, black holes, and the formation of galaxies. Later, other telescopes followed, such as Chandra, X-ray astronomy, Spitzer, infrared, and, most recently, the James Webb Telescope, 2021. This made astronomy multispectral. The sky was explored in all wavelengths. Space probes, ambassadors into space. Space probes made it possible to explore planets and moons directly. Voyager 1 and 2, 1977, traveled past Jupiter, Saturn, Uranus, and Neptune. Voyager 1 is now in interstellar space. Pioneer probes carried messages to possible extraterrestrial civilizations. Cassini-Huygens explored Saturn and landed a probe on the moon Titan. New Horizons flew past Pluto in 2015 and showed detailed images of the dwarf planet for the first time. These missions fundamentally changed our understanding of the solar system. Man in space. Manned space travel is still a symbol of human thirst for research today. After the Apollo moon landings, the focus was on space stations such as Mir, Skylab, and the ISS. Astronauts researched the effects of weightlessness, conducted experiments, and repaired satellites in orbit. Private companies such as SpaceX or Blue Origin are opening up new perspectives on manned missions to the Moon and Mars. Humans themselves have become active participants in space. Exoplanets, discovering new worlds. Since the 1990s, one of the greatest discoveries in modern astronomy has been made: the existence of exoplanets, planets outside our solar system. In 1995, Michel Mayor and Didier Queloz discovered the first exoplanet around a sun-like star. Since then, more than 5,000 exoplanets have been confirmed. Methods such as transit observations, Kepler satellite, or radial velocity measurements make it possible. Many exoplanets are located in the habitable zone, where liquid water could be possible. This brings the question of extraterrestrial life closer. International cooperation. Space also promoted international cooperation. The International Space Station, ISS, is a joint project of the USA, Russia, Europe, Japan, and Canada. Large-scale projects such as the James Webb Telescope or the Euclid mission show that modern astronomy only works globally. China, India, and other countries are also increasingly investing in space travel and astronomy. The cosmos became a common project of humanity. Astronomy in the digital age. Modern astronomy would be unthinkable without computers and data analysis. Huge amounts of data from telescopes are evaluated with artificial intelligence. Citizen science projects enable lay people to participate in discoveries. Simulations and models make it possible to trace the development of the universe. Astronomy today is not only observation, but high technology. Conclusion: the age of space travel. With space travel, humanity entered a new era. Satellites and space probes made the cosmos tangible. Space telescopes opened up a view into the depths of the universe. Exoplanets and international missions expanded our understanding. Today, more than ever, astronomy is a global science, and space travel is its practical arm. Together, they show that humans are not just spectators, but active participants in the universe.
Chapter 12. Astronomy Today. Black holes, exoplanets, and dark matter. Astronomy in the 21st century is at a turning point. With state-of-the-art telescopes, supercomputers, and space probes, it is possible to explore the cosmos more deeply than ever before. At the same time, we come across mysteries that leave fundamental questions unanswered. What are black holes? Is there life on exoplanets? What are dark matter and dark energy made of? Today's astronomy moves between fascinating discoveries and great unknowns. Black holes, the most extreme objects in the universe. For a long time, black holes were only a mathematical consequence of the general theory of relativity.
Today, we know they are real. Black holes are formed when massive stars collapse. Their gravity is so strong that not even light escapes. They shape the evolution of galaxies by devouring matter and emitting high-energy radiation. Observations. In 2019, the first photo of a black hole at the center of the galaxy M87 was taken by the Event Horizon Telescope. At the center of our Milky Way is Sagittarius A star, a black hole with about 4 million solar masses. Black holes are not only exotic objects, but keys to understanding gravity and space-time. Exoplanets. Search for a second Earth. The discovery of thousands of exoplanets has revolutionized our view of the universe. There are hot Jupiters close to their stars, Earth-like planets in habitable zones, and even systems with multiple habitable worlds. Missions such as Kepler and TESS have found hundreds of candidates for Earth-like planets. The James Webb Telescope is now studying the atmospheres of some exoplanets, a first step in the search for biosignatures. The question, "Are we alone?" is no longer just philosophy, but an empirical research question. Dark matter, the invisible scaffolding. Another big mystery is dark matter. Galaxies rotate faster than their visible mass allows. Galaxy clusters stick together, although they should actually fly apart. Gravitational lenses show more mass than we can see. The solution? There must be an invisible form of matter that accounts for about 85% of the total mass of the universe. So far, no one knows what dark matter is made of. Candidates are hypothetical particles such as WIMPs or axions. Dark energy, the biggest mystery of all. Dark energy is even more mysterious. In 1998, astronomers found that the expansion of the universe is not slowing down, but accelerating. To explain this, a form of energy has been postulated that drives the space itself. Dark energy makes up about 70% of the universe, and we know almost nothing about it. This means that over 95% of the universe consists of something we don't understand. Gravitational waves, a new astronomy. In 2015, the LIGO Observatory achieved a historic breakthrough, the first direct observation of gravitational waves. Gravitational waves are tiny ripples of spacetime caused by collisions of black holes or neutron stars. They open up a completely new way of observing the universe, not with light, but with spacetime itself. They can be used to research events that were previously invisible. This marks the beginning of a new era of astronomy. Multi-messenger astronomy. Today, astronomers combine different types of observations. Light in all wavelengths, radio, infrared, X-ray, and gamma, gravitational waves, neutrinos, almost massless particles that originate from cosmic explosions. This multi-messenger astronomy allows a more comprehensive picture of the cosmos, like an orchestra of different signals. Major international projects. Today's astronomy is global and gigantic. James Webb Telescope looks into the beginnings of the universe. Euclid mission, ESA, research into dark matter and dark energy. Square Kilometre Array, the largest radio telescope in the world, under construction in Australia and South Africa. Vera Rubin Observatory will map billions of galaxies. Projects like this show that exploring the universe is only possible through international cooperation. Astronomy and artificial intelligence. The data volumes of modern astronomy are gigantic. Telescopes produce several terabytes of data every day. Artificial intelligence, AI, helps with the analysis, pattern recognition, and detection of exoplanets or gravitational lensing. Citizen science projects such as Galaxy Zoo involve laypeople to cope with the flood of data. Astronomy today is a science of big data. Conclusion: between knowledge and ignorance. Astronomy in the 21st century has made tremendous progress. We can photograph black holes. We are constantly discovering new worlds around distant stars. We measure gravitational waves and see the universe in a new way. And yet, we hardly know what the cosmos consists of at its core. Dark matter and dark energy remain unsolved mysteries. Today's astronomy is caught between deep knowledge and great ignorance, a fascinating tension that continues to drive research.
Chapter 13. Looking to the Future. The Next Centuries of Astronomy. The history of astronomy is a history of constant surprises. Again and again, new discoveries have overturned old worldviews. From the geocentric cosmos of antiquity to Newton's clockwork universe to the expanding universe of modernity, each age had its own answers. But the biggest questions are still open. How will astronomy develop in the coming centuries? New telescopes, windows into the depths of space. In the coming decades, new instruments will change our image of the cosmos. James Webb Telescope, JWST. It already provides spectacular images of distant galaxies that were created shortly after the Big Bang. Its data could completely rewrite our understanding of the early history of the universe. Extremely Large Telescope, ELT, Chile. With a 39-meter mirror, it will be the largest optical telescope in the world. It is intended to directly image exoplanets and study their atmospheres. Square Kilometer Array, SKA. The world's largest radio telescope, under construction in South Africa and Australia, will map billions of galaxies and study dark matter. These large-scale projects show that we are only at the beginning of what can be observed. Exoplanets and the search for life. One of the greatest hopes of the coming astronomy is the discovery of extraterrestrial life. With improved telescopes, we will be able to examine the atmospheres of exoplanets for biosignatures, such as oxygen, methane, or water vapor. In the next 50 to 100 years, we could find the first clear evidence of life outside Earth. This would be a discovery that would radically change the way we see ourselves as humanity. Whether we will ever encounter intelligent life remains open, but the search has long been a serious scientific mission. Dark matter and dark energy. Perhaps the greatest mysteries of cosmology are dark matter and dark energy. With new detectors in laboratories deep underground, it is hoped to detect dark matter particles. Projects such as Euclid or the SKA are intended to map their distribution in the universe. Dark energy could be better understood through precise measurements of expansion. Perhaps it will become the foundation for a new physics beyond Einstein. A breakthrough in this field could be as revolutionary as the theory of relativity or quantum mechanics. Interstellar space travel. While astronomy sharpens the view into the distance, the dream of traveling there oneself is also growing. Projects such as Breakthrough Starshot want to send tiny laser-driven probes to the star's Alpha Centauri. Travel time around 20 years. In the distant future, nuclear fusion or other technologies could make interstellar travel possible. In this way, humanity could go from being an observer to a participant in the cosmos. This is still a dream of the future, but the history of space travel shows how quickly visions can become reality. Gravitational waves and the multi-messenger age. The future of astronomy will also use new observation channels. Space detectors such as LISA are designed to measure gravitational waves in space and receive signals from black holes or the early universe. Multi-messenger astronomy becomes the standard. The combination of light, gravitational waves, neutrinos, and cosmic rays provides a complete picture. We will not only see the universe, but also hear and feel it. Man as a cosmic species. Astronomy is not only a science, but a vision. With lunar bases, Mars missions, and perhaps colonies in the solar system, humanity could become a multi-planetary species. Astronomy not only provides the technical basis for this, but also the philosophical framework. We are part of a cosmic process. Looking at the sky reminds us how small we are,
and how great are possibilities. Philosophical dimensions. The astronomy of the future will not only provide new data, but also raise new questions. What does it mean when we find life on another planet? Will we one day know the last theory of the universe, or will the cosmos always remain a mystery? What role does humanity play in a universe that is unimaginably large and old? Astronomy is therefore also a search for meaning, and always will be. Conclusion: the next revolution is waiting. The history of astronomy shows that every generation discovers something that changes everything. Antiquity created the first cosmic models. Copernicus questioned the Earth. Newton explained celestial mechanics. Einstein and Hubble opened up the view of the expanding universe. Today, we are faced with the mysteries of dark matter, dark energy, and exoplanets. The next centuries will bring new answers and new questions. Astronomy is a journey without end.